Lewis structure for carbonate. That's what we said we're going to start with, and we're going to come back to that structure again when we look at shapes. So you need to be able to follow the rules. You don't have to follow my rules, you just have to get the answer right. My rules tend to get you to the answer, in my opinion, smoother than what the textbook suggests, but that is entirely up to you, if you want to follow those or not. So let's take a look at carbonate. Carbonate has what formula? You should have that one memorized. I'm pretty sure that's one of the ones I told you to have memorized, the carbonate ion. Okay? Some things that you need to remember is that -2 charge. We will come back to that a whole bunch, so please be aware of that. Our first step is to do what? Valence electrons. How many valence electrons does carbon bring in? 4 valence. How many electrons does oxygen bring in? How many of them are there? Now we have to account for our charge. Whoops, shouldn't do the plus quite yet. What's our charge? -2, which means we had to add 2 electrons into our structure. This gives us our total valence, which is, what did you guys say it was? Thanks. I didn't feel like adding. Pick our center atom. What's our center atom? Why carbon? It's the least electronegative. Okay? Other things we could do, particularly if you were doing your lab assignment, and it kind of works. A lot of the lab assignment problems start with the center atom. It's not always the case in the formula. In this class, as far as the lecture goes, your center atom should be the least electronegative. That can still bridge. Okay, so carbon's the only one that can do that. We'll scatter our other atoms around it. Up to you how you want to do it. Ultimately, I know the answer, so I would probably scatter them perfectly symmetrically. Since, in theory, you don't know the answer, let's go ahead and pick kind of the 3 sides. What do we do now? We put in our electrons starting with the oxygens. Why? They are the most electronegative. How many electrons do we put in around oxygens? Why do we put 8 in? It's our octet rule. We continue to go. More and more and more and more electrons. How many electrons do we have? We've got all 24 electrons. Okay. What's our next step? I agree with drawing bonds. I don't agree with valence. How do you draw bonds? We'll come back to the valence question in a second. When do you know to put in a line? 2 electrons between atoms. Okay, now back to your valence question. What did you mean by valence?
Make sure they don't have 8 electrons.
I would recommend you draw the bonds first. Okay, so then the next step, and since that looks like a bad single arrow, let's fix that. The next step would be checking octets. Okay, and I want to step away from valence. It's the octet that we're verifying, not the valence electrons. So we now go through and determine, do we have our octet satisfied? So we check with our oxygens. What's the deal with our oxygens? Oxygens are all okay. We've got 3 non-bonding pairs of electrons, which gives us 6. And then we have the line coming off. So we're looking at another 2 electrons. All of our oxygens have their octets. The carbon, however, does not. Okay? Carbon only has 6 electrons. How do we fix that? We need to... I don't like the statement, we need to make a double bond. It's not technically wrong, I just don't like it. Okay? The statement that I would prefer is that we say we have to move electrons towards the carbon. Okay? Which means we'll have to share another pair of electrons. The end result is a double bond. Okay? Very, very subtle difference in the terminology. It makes a huge impact in organic chemistry. Okay? So I really am trying to emphasize that phrasing a little bit more. So what we can do is take a pair of electrons that's nearby and shift them towards the carbon. So we'll put them into a new bond. which pair of electrons do we move? Okay. In this case, they're all the exact same. There is no difference between those oxygens, which means it doesn't matter which one we use, sort of. So let's take the left one and we shift those in. So what we could do is show an arrow showing that new drawing, or how we're going to get to that new drawing. But now we actually have to draw that new drawing, and we would have our double bond. Okay. Problem with that is that we haven't addressed that any of the other oxygens could have just as equally done it. Okay. Which means we also have to draw those other possibilities. Okay, and that's what resonance is looking at. Okay, I saw your hand first, Thor, and then Lindsay.
Is there any time that we wouldn't do the lines for bonding, or just leave them with the electron pairs?
In the lecture, no. In the lab, yes. The lab specifically requested electron dot structures and then molecular structures. Molecular is looking at the bonds, so you'd want to see those lines. The lab assignment asked for the dots. I don't know why. At least the way I'm showing you to go through and do it, you end up erasing the dots to make your bond anyway. So what they've done is really broken down those individual structures.
So for exams and whatnot, you could...
For exams, the only thing I'm looking for is the molecular structure. Okay, so even if I say Lewis dot structure, what I'm looking for are the bonds. Yeah. Not quite there yet. We still have hands. Yes, Lindsay.
Does symmetry matter at all with this?
Yes and no. So what do you mean by does it matter?
Like with the quantity most preferable way to draw it with the two lines in the middle.
So with the bond angles that we've got drawn on here, where we've got those 3 or 4 sides to it, we could say, yeah, that makes the most sense. However, do we have those exact bond angles? Okay, if we looked at the shape, which we'll look at in a second, we drew that technically wrong. Those 3 oxygens need to get as far away from each other as possible, which means the shape that we have ends up coming out to be trigonal planar. So if we put the double bond here versus here, can you see the dots? Sort of. Versus over here. In all cases, it's equally symmetrical. Okay? So we don't see a symmetry argument in that case. Yeah, Mark.
So for like future tests and whatnot, would you want us to do all 3, or would you want us to?
So if I ask you for the Lewis structure for carbonate, what's your answer? You have to specify all 3. Okay? So what's the likelihood I'm going to give you a question that involves lots and lots of resonance?
Slim.
Very, very slim. You'll probably see one problem where you've got resonance and very limited amounts of it. So at most, probably 3 structures. Okay? If you have to move further on into organic chemistry, you can push questions up to 5 or 6 different structures. Okay? Other questions about what we've done so far? Last step. What's that? We need to specify the charge. So we can go through and put in our brackets and put in the -2. Lazy way. I know that looks like a 7, but that's ultimately a bracket. And we'd have to specify that with each of these. Okay? So one of the simplifications that we can do or get away with at this point is we can specify the charge on the entire molecule. We don't have to determine which atom is charged, or atoms for that matter. Okay? You will learn how to do that in this chapter, officially chapter 17. Okay? But you won't have to apply it back to your Lewis structures. Questions about carbonate? Okay. So Lewis theory does a great job explaining the overall bonding, but he doesn't do such a great job explaining the 3-dimensional structure. Okay? And really the limitations there come from just being able to draw. We're trying to draw in 2 dimensions something that exists in 3 dimensions. So our perspective on the drawings gets a bit questionable and we lose some interpretation. That's where valence shell electron pair repulsion theory comes in, or VESPR. So what they went through and did with that theory is said, okay, we've got the basic outline of what Lewis is giving us, where all the electrons are located. Now what we're going to do is predict what would happen with those electrons. We know they want to get as far away from each other as possible. What three-dimensional shape is generated in that process? Okay? We end up getting two subcategories when we look at our VESPR theory. You get electron geometry, and you get molecular geometry. Okay? Depending on the circumstance or the question, you may have to answer differently in each of those cases. Primarily, we're going to be concerned about, actually I changed my mind. I will probably only test you on the electron geometry. I want you to be aware of the molecular geometry. I'll have to take a look at the final to see what's going on with that, see if maybe we need have you memorize the molecular geometries. But at this point, I'll have you memorize the electron geometry. And what I would expect you to be able to do is there a difference between the electron geometry and the molecular geometry? Okay, so you won't need to tell me what that exact shape is, because they get a new name, but can you tell me, is there a difference? Okay? So let's go through and take a look at a couple examples. So we can look at our electron geometries first. If we look at representative molecules, you should be able to go through and draw Lewis structures for these. I will point out that the last two structures are more difficult than anything you've seen so far, and I'm pretty sure you are officially not responsible for those this class. Okay? But be aware that we can do something called exceeding the octet. Fairly rare, but it can happen. Okay? So if we start with HF and we look at its electron geometry, what we would do is draw out our Lewis structure. Okay? And depending on what atom we looked at, we'd look at differing numbers of groups. Since I said there's only one group of electrons, which atom am I deciding is my center? The hydrogen's got to be my center atom in this discussion. Okay? Why? Because I'm defining that there's one group of electrons here. So if I'm using this as an example, I better pick one that has one group of electrons. So hydrogen would work in this case. Where's that one group of electrons around the hydrogen? Okay, it's only in the bond. Okay, since I'm seeing some quizzical looks, let's go ahead and just see what would happen if we said fluorine was our center atom. Okay, if we call fluorine our center atom, how many groups of electrons are now around it? We get one group in a bond, in the bond, and then we get three groups as non-bonding electrons. So when we're evaluating our groups of electrons, for the most part, all we will see is 4. Remember, we do get those weird exceptions up with 5 and 6, but you're ultimately, again, not responsible for those. You're responsible for interpreting them, not necessarily going beyond that. Okay? So if we looked at fluorine, we'd have to say 4 electron groups. That puts us in a different category. Okay? For the sake of this argument, we were trying to look at a case where we had just one electron group. If we look around hydrogen, hydrogen only has that one group of electrons. Okay? Questions about HF? Good. We can move up to 2 groups of electrons. So I picked magnesium chloride in this case. And what we could go through and do is, again, try and draw out a Lewis structure. And if we picked our center atom in this case, what's our center atom? A little bit easier to see in this case. It's our magnesium. What are the groups of electrons around it? Look at the 2 bonds around it. We've got 2 groups of electrons. The shape that's going to come out of that is linear. Okay, why? Well, those 2 groups get as far away from each other as possible. The max distance they can get is 180 degrees away. Okay? So we're looking at that linear shape. What if we went through and did BH3 or CH4? Okay? Again, what we're trying to do is get those electron groups as far away as possible, and we end up generating a new shape. Okay? How do we decide what that new shape is? And that becomes a little bit tricky. To really do that, we'd have to manipulate a movable arrangement of atoms that are all connected to each other so that we could verify that that is indeed what happened. Okay? Or you're wicked good at geometry. I think it's geometry. I can tell you right now, I'm not one of those people, and so I just accept that someone better than me went through and decided what these shapes were. Okay? Questions about these overall electron geometry shapes? Okay. One of the other representations that we could get, which you'll see at least on my slides, okay, we can look at our center atom in red in this case, and then those side groups of electrons in green. Okay? If you move further on into chemistry, you'll see this orbital depiction, which is what's shown in blue. Ultimately, all again we're trying to do is come up with some way to accurately reflect that three-dimensional structure as best we can. It's not the easiest, but that's kind of what we're responsible for trying to go through and do. Yes?
So, since on the next one,
Yep.
boron only has 3 valence, and then there's 2 for each hydrogen, there's 3 hydrogens.
So I believe what you're asking is we should draw that one?
Yeah. Only because it needs a valence of 8, how is it going to do it with sharing? So there's
BH3, electrons that boron brings in. Electrons that hydrogen brings in. 1, there's 3 of them, which gives us a total of 6. So we would now go through and try and put together our structure. Our center atom will have to be boron. Put on the hydrogens. And then we'll now put in our 6 electrons. We're going to start putting those 6 electrons where we have atoms, because we know we need to put in bonds. We put in all of our electrons. Will we put in all the electrons? Yup. Now we can turn them into bonds. And now we can go back to your original question, the octet rule. Does hydrogen have its octet satisfied? Does boron? Boron's a bit weird. What's a bit weird with boron? Doesn't have its octet. Do we have any more electrons that we could possibly put into it? No. What's our Lewis structure? That's it. Okay. So if we don't have the electrons, then we're short. So what does that mean about boron?
it needs its amount, but it doesn't have 8. Oh, but it only has 6 valence.
Everybody's upset with boron not having 8 electrons, right?
Yeah.
How many of you are upset that hydrogen doesn't have 8 electrons? Nobody?
Well, what
So why do you care that boron doesn't have 8 electrons?
hydrogen is supposed to be the only exception.
Hydrogen was supposed to be our only exception. That doesn't mean it is the only exception. Boron has very interesting chemistry in that it's happy at 6, but it can get to 8. How would it get to 8? Something else would have to contribute the electrons. What type of bond would we be making if something else contributed electrons to boron? It's not quite covalent. It's not ionic. We talked about it very briefly. If we bring in 2 atoms into an individual bond, one has a hole, no electrons contributed to the bond, and the other one brings in 2 electrons. It was known as a coordinate covalent bond. Boron is a species that does coordinate covalent bonds very, very well. Is there another element you might predict that could do coordinate covalent bonds very well? Aluminum. Why aluminum? Directly below boron, it has the exact same chemistry. So good question. Boron's a bit weird, which makes its chemistry very interesting, particularly if you move into organic chemistry. Okay? Sorry. Did that answer your question on that?
Yeah.
Okay. Other questions with the electron geometry? Okay, remember what you need is tetrahedral, trigonal planar, and linear. Those are your 3 main shapes based on the electron groups 4, 3, 2, and officially 1. Yes?
That's probably obviously bad, but the second one, the magnesium chloride, why does it show 5 4 element?
You're right. It's a bad copy-paste job on my part. Yeah, that's really bad. I should have caught that. We should have doubled on the linear. Yeah, the linear should have doubled. That one goes for the magnesium chloride, and there should be one for HF. Here, let's draw it real quickly. Red dot, green dot, bond. Actually, it's only that. And there's our linear shape. Oops, that's an eraser. Good catch, I didn't see that. Other questions on that? So everything should shift down by 1. So your linear, your first linear applies to the magnesium chloride, your trigonal planar, BH3, tetrahedral, CH4. So I did assign the electron geometries correctly. The images just don't match up right. Other questions on that? Okay. So then the question is the electron geometry our final spot? Do we need anything more than that? Well, if we take a look at ammonia, NH3, we might start to predict something similar to BH3. Why? At least superficially. Formulas are the same. We might expect something very similar. But when we go through and draw our Lewis structure for ammonia, you should end up with something like this. So now that is distinctly different from our BH3. We have an extra pair of electrons in there. How many groups of electrons are around the nitrogen as our central atom? We've got the non-bonding pair and 3 bonds, which gives us 4 groups of electrons, which would say our shape is tetrahedral. That's close enough to spell it. Okay? What ends up actually happening? Well, if we look at the molecular geometry, we don't actually get a strictly tetrahedral structure. And that's ultimately coming from our ability to not see electrons. When we look at a structure, when we look at the molecular geometry, what we're concerned about are the atoms. Okay? And so when we look at the structure of ammonia, we don't have that cap tetrahedral structure that we would get from, say, methane. So the geometry changes a little bit, and we have to call it something else. Okay? And that's ultimately coming from the big difference, a bond versus a not bond. Okay? If we have a pair of electrons that are not involved in a bond, those electrons are in a different space than the electrons that are in a bond. Okay? The example that I would go through and use, since you're closest, I'm going to stick with you. Okay? If these are my 2 electrons, and we're looking at it as not a bond, I'm holding on to them. They are very, very close to me. What happens if I now decide to share? Go ahead. You can take one. If I decide to share, the electrons start to get a little bit further away from me. Okay? That change in the distance is ultimately what's causing that bond shape. Okay? The angles between all of those atoms, you still want it?
No.
Okay. Those shapes to change a little bit. That change, since it changes the shape, we now come up with a new name to describe that overall shape. So when you're looking at the molecular geometry, it's because the electrons have changed their positions. They're no longer all the exact same, which means we see a slightly different arrangement of atoms. Yes?
Okay, so on these, with the bonds like this, when we talk about the radius, since the electrons are being shared, would the radius be smaller than
I think you're going to make that way more complicated than you want to deal with.
and then
I'd
the shape,
get rid of the radius argument.
the shape, it holds the same shape, but the whole thing together spins, like, or moves around?
I think, again, that's going to be not a question that you want an answer to. As a first approximation, yes. The whole thing can now spin and rotate in 3-dimensional space.
Did it, like, say we make a double bond between the...
We'll look at the double bond in a second. But, yeah, that's a good question as well. So what ends up happening? We've got our electron geometry, so our 4 groups of electrons. Okay? But now when we move to our molecular geometry, we have a slightly different shape. Okay? The example that I like to give most is using my hand as a tetrahedral as a tetrahedral structure. Let's see if I can do that again without it cramping. My wrist is an atom, and then each of my fingertips is another atom. Okay, so we'd have a tetrahedral structure where my center knuckle is the center atom. So this could be CH4. Okay? If we now decide that my wrist is no longer an atom and those electrons get pulled closer to the structure, okay, because it's now not in a bond, what ends up happening? Okay? Well, we've matched out a 109-degree angle between each of those atoms. If we now bring this electron group closer down, what happens to each of these? Okay. Should they spread or should they shrink? What does my finger represent? Electrons. If I bring electrons closer to that electron source, what happens? They repel. So if I bring electrons closer down, where do my fingers go? They come tighter in. If they spread out, what happens? I just brought them closer to my electron source. So here's my electron source, my finger. If I bring it down and I spread, my bonds just got closer to my finger. If they shrink, what happens? They get a little bit further away. Okay? So it's a little bit hard to visualize, particularly when using my hand. Okay? But if you get a model kit, it's even harder with the model kits because they don't bend. Okay? So what we're looking at is that slight tweak in shape, and that's where we end up refining. Instead of going with just our electron geometry, we now have to decide, are those electrons all the same, or are they different? In the case of ammonia, we have a bonding pair or we have 3 bonding pairs of electrons and 1 non-bonding. So what we would have to go through and do is say what changes about that structure. It's still ultimately 4 groups of electrons. They're just different. So we would move into the tetrahedral category, but now one of those groups is not a bond. So if we take a look at our images, what we're saying is that this group of electrons is not being shared with another atom. What happens? When we look at the molecule, we don't see that tetrahedral shape. Okay? We see ultimately a pyramid with our red atom being the peak, and it's a triangle. We have a triangular shape. Why is it not triangular planar? Because it has that extra pair of electrons that we circled in purple. That extra pair of electrons prevents it from flattening out.
For the boron one that we did,
Yes.
on our chart it said trigonal planar, but on the chart in the book, that's when there's 4 bonds and 0 bonds. It says 4 bonding and 0 bonding.
For what compound?
For BH3.
They're wrong. It's a typo.
Okay.
Absolutely.
Because I was like, let's try.
Yeah. BH3 has 3 groups of electrons. We'd move into the trigonal planar category. All of those electrons are exactly the same. The geometry, the molecular geometry around boron is trigonal planar.
It makes sense with the
Yep. So yeah, I would guess the textbook was looking at something else. I'd have to look at it a little bit closer to see. So you can show me after class. Okay? Ideally, you know everything above that red line. Okay? You should be able to apply any Lewis structure and get the general shapes coming out of that. Okay? Both the electron geometries and that trigonal pyramidal and the bent. Okay? Ultimately, in my opinion, you're really only having to memorize 1, 2, 3, 4, 5 things, okay, with those relative shapes. That shouldn't be too difficult. You guys should be able to predict that without too much of a problem. Again, I'll have to see what the final is expecting of you, if you're expected to have that memorized or not. Okay? Questions overall about these shapes, at least the simple ones? We are going to look at 2 trickier ones in a second.
You're saying we don't need to worry about memorizing sawhorse, T-shape, trigonal, binomial?
Anything under that red line, absolutely do not memorize. I don't think I saw any of those shapes in the textbook. They weren't directly addressed. You will have to see those if you move into 151 is where they talk about it next. Okay, so you won't need to worry about it right now. So let's take a look at some tricky molecules. Carbonate. You all remember one of the structures of carbonate. Why do I not need to draw all three right now? Kind of comes back to lazy. What's our electron geometry going to be for all three? Exactly the same. It doesn't matter which of those three structures we look at. We're going to get the exact same electron geometry, the exact same molecular geometry. So I don't need to draw all three at this point. Okay? And you'll notice I'm also going to ignore the charge in this case. Why? Because all I care about when we're looking at shape is what's happening around my central atom of carbon. Okay? And this is where these become a little bit trickier. Okay? How many electron groups do we have around the carbon? We have a bond there, that is absolutely 1. We have a bond here, that is also absolutely 1. What happens when we get up to here? Why does that only count as one group of electrons? Where are those electrons located? What makes a group of electrons unique? It's located between a different space, okay? Either between the nitrogen and the left oxygen, or, sorry, that's a carbon. Carbon and the left oxygen versus carbon and the right oxygen. Those electrons are in a different space. What about the electrons in the double bond? They're in the exact same space. Okay? So what does that mean? It's one group of electrons. It just happens to be a really big group. Okay? So with that analysis, how many groups of electrons do we have? 3 groups of electrons, which means our electron geometry is, we've got trigonal planar, and our, man, that takes a lot to write out, molecular geometry. We would go into our trigonal planar category and decide, okay, that one extra case is saying we have a lone pair of electrons or a non-bonding pair of electrons on our center atom. Do we have that? Nope. So what is the geometry? It's exactly the same as our electron geometry. It's trigonal planar. Okay. Questions? You want another example or you think you got it?
Yeah.
No, I want to know.
Okay. Sorry, but this is going to be your last example. If we went through and did CO2, okay, you should be able to follow your rules to figure out your Lewis structure for CO2. You'll notice okay, fine. I need to be more careful with that. I'll follow all the rules. Carbon has 4 electrons. Oxygen has 6. There's 2 of them, which gets us 16, right? Carbon's our center atom. Scatter the oxygens around, put our electrons around our oxygen first. We'll notice that we have a pair of electrons in between our oxygen and carbon. We can convert those into a bond. Whoa, that's an ugly looking bond. Our carbon doesn't have its octet satisfied, so what do? We'll shift a pair of electrons in from each side. Why do we go from each side? It's ultimately for looks. Well, it's not officially for looks, but as far as you guys are concerned, it's for looks. We're getting symmetry, and we now have our Lewis structure for CO2. Yes?
So the electron pair geometry, does that get based on the number of groups being grouped together?
The electron pair geometry, or
Like that would be tetrahedral because it has 4 bonds.
pick your center atom. So when we decide on any shape, you must pick a center atom. So pick the center atom that you are going to work with. Okay. In this case, it's carbon. How many groups of electrons are around the carbon? We have 4 bonds to get to the octet, but we do not have 4 groups. Okay?
So based on the bond, how many bonds?
Can't do bonds. There's still 4 bonds around carbon. So it's a group of electrons. Is it a unique group of electrons? Are those electrons in a different space than another group of electrons? Okay? So how many groups of electrons are around that carbon? Two groups, which means we're looking at linear as far as our electron geometry goes. We would then take it a step further and look at the molecular geometry. Do we have any non-bonding pairs of electrons? On the carbon. So center atom. Always stick with the same center atom. Around the carbon, no. What's the geometry? Still linear, no change. Okay? And since I'm seeing a little bit of quizzical there because you're asking about the non-bonding pairs, let's push this a little bit further. Let's decide that carbon is not the center atom. Okay? We should hopefully all agree that carbon is. As far as the exams go, I will specify what center atom I want you looking at so we can minimize that ambiguity. Okay? But let's go through and decide that oxygen is our center atom. So we'll do this one in green. Okay, if oxygen is our center atom, how many groups of electrons are now around it? We've got our group of electrons for the bond. We have a group for a non-bond and a group for a non-bond. We have 3 groups of electrons around the oxygen. What's our electron geometry? We're back to our trigonal planar. And this is where this figure dies out. When we take a look at that, and we now want to push it to our molecular geometry. Okay, we would look at our trigonal planar line, and we'd try and find the category where we had 2 groups of electrons. Okay? It didn't show us 2 groups of electrons. Why? What's the geometry? There's only one bond. So what we're looking at is a linear geometry.
So for the electron one, it's based on the groups around the center.
The electron geometry is based solely on your center atom. The molecular geometry is still based on your center atom, whatever you've decided that center atom is. The issue with the figure here, and it's ultimately because it's copied out of a book because they can draw better than I can, you don't see some of the other options. Okay? And that's because what did the book decide? Those were trivial and they didn't want to show them. That was it. Okay? I don't have the ability to draw nice and neatly like that, so we can look at another way to format it. And I'll come back to your question in a second here, Netsai. We can look at our shape summary. Look at your electron groups. Your electron pair geometry is linear. Okay? What are your possible options at that point? Well, you really only have a bonding pair of electrons. You won't have any non-bonding pairs of electrons because there was only one group. Okay? If there wasn't a bond, then we wouldn't even be looking at a bond. Okay? So our shape in that case would be linear. What happens if we have 2 groups of electrons? Our electron geometry is again linear, but now we can start to evaluate what's happening with bonds versus non-bonds. If both of those groups of electrons are a bond, then what we're looking at is no non-bonding groups because we could only have 2. It has to be linear. What if one of the groups was a non-bonding pair of electrons? Still going to be linear. There's no other molecules or atoms around it. What happens when we move into trigonal planar? Okay. Again, you can go through and look at all the possible combinations to generate those individual shapes. You'll notice that even I was a little bit lazy. I didn't, never mind. I actually did a pretty good job. Because we're still trying to show those bonds. At no point do we show up with a non-bonding or a bonding group of electrons that's 0. Why? What's our shape if we don't have any bonds? It's just the atom. We can't even really call that linear because there's nothing for it to be linear with. Okay? So to me, this summary covers pretty much everything you would deal with. The biggest issue that I have with this, any guesses? No colors, no pretty pictures. But this will answer pretty much any question that you might have if you follow it according to your electron groups. Get into that subcategory and then evaluate bonding versus non-bonding. What was your question? Betsy, you still have your question?
I got it.
Okay.
So non-bonding linear.
Questions about your shapes? Much like nomenclature and Lewis structures, really what it's going to involve is a little bit of practice. I would say it's going to involve less practice than Lewis structures or nomenclature, but once you start getting used to the patterns, you should have pretty much these individual sections memorized pretty quickly, and you'll be able to process them pretty swift. Questions about any of that? Okay. That means I got a quiz. So go ahead and get the notes away. Give you till 9:10, which is roughly 4 minutes. Let me know if your road isn't good enough. I'll come back around to you. And I'll come around and grab it. Just worry about the quiz. I guess chapter 7. I can accept chapter 7. So the current slide set, depending on when you downloaded it, it may have changed. As of 7 o'clock last night, I believe, maybe 6:30, all of these slides are chapter 7. Okay, so the entire chapter 7 is up there now. So I'm going to be using this for probably Thursday's lecture as well. The only thing that might change is I'll put in an extra quiz slide. Now you just won't know what that quiz is. Boo-hoo. The next issue is the homework. Homework is posted to Canvas because I believe it was actually someone from the afternoon pestered me enough that I actually went through and picked questions for all of the chapter assignments. Okay, so chapter 7, 17, 8, and 9. Everything is up there, okay, on Canvas right now as far as the exam 3 homework goes. I'll try and make sure it makes it into the slides too. I just didn't try to copy and paste it and it didn't work.
Can I bring in my homework each week and just have you look at it?
You can absolutely bring by your homework each week to have me go through and take a look. I will say that the first 5 minutes of class, or even the first 5 minutes before class starts, will be an open question session. So if you have questions, that's when I'll answer them. And I'll let that carry 5 minutes into class, and then we're starting. All right. We're definitely not being as efficient as we need to with time, so that's just going to be the way to work. Office hours, for sure. Everybody keeps asking, like, when am I here? I'm physically on this campus roughly 50 hours a week. Okay. That doesn't mean I'm only doing work here, too. I'm also working when I get home. So if you need to find me, I am here. I can help. You just have to make sure you ask for it. Mondays and Wednesdays, office hours are 11 to 12:30, roughly. Tuesdays and Thursdays, it's 2:30 to 4. And then Friday's a bit spotty, and that's why it's not posted anywhere. It's usually about 9 to 11. It really depends on just meetings. So like this Friday, I'm pretty sure I'll be here 9 to 11.
What was Wednesday?
Monday, Wednesday is 11 to 12:30. Okay. And then appointments. Set up an appointment.
You don't have to.
Tuesday, Thursday is 2:30 to 4.
Oh.
So I get a half hour for lunch at 2. Okay. So chapter 7. What are we looking at for chapter 7? They do a quick review of chemical versus physical changes. We briefly talked about it in some earlier chapter. I don't even remember what that chapter was. But there was kind of an awful description of it because you didn't have any understanding of molecules in theory at that point. Okay, so we just kind of made up some rules and you kind of had to take a stab at it. So we're going to come up with slightly better definitions when we look at our chemical and physical changes now, because we're going to start to learn more about what makes a chemical change. Okay? Your physical change, the substance stays the same. Okay? So it's the same molecule, but we've changed its phase. So liquids to gases, solids to liquids. Sometimes dissolving is considered a physical change. Okay? Chemical changes, we're changing the chemical composition. So we're changing the arrangement of atoms. If the atom arrangement changes, it's a chemical change. Okay? Not the easiest thing to go through and see or work with, particularly at the beginning of the semester. Okay? So for instance, dissolving sugar, physical or chemical? That one's physical. Dissolving salt. There's a really strong argument that that is chemical. Okay, why? When you dissolve salt, you don't get molecules of sodium chloride. You get atoms of sodium ion and chloride ion separated by water. How would you know that? Good freaking question. Okay? So that line between chemical and physical really requires a pretty deep and thorough understanding of what's actually happening within each of those solutions. Those kind of weird gray areas we'll try and leave off of tests, and if I see them show up on the final, I won't tell anybody, but I'll pull those questions from being counted as points. Okay? Because ultimately, if I tell you, then you'll tell somebody else, and then I get yelled at by the rest of the faculty. So if it happens, I'll pull it, but just not tell anybody that I pulled it. Okay? So with our physical and chemical changes, is that an actual question there?
Yes.
Yes, fire away.
So when you heat something up and it just changes color?
So again, deciding on what's happening with chemical versus physical. So it can help to have a better understanding of what your physical changes are. So what are the observables that you would see to allow you to decide, is that a physical change or a chemical change? Okay? The biggest one, so your textbook broke this down into 4 rules, though I would argue rule 1 and 2 are the same. What we're looking at is a change in phase. Okay? With one big caveat in that. The change in phase cannot involve you adding or subtracting heat. Okay, why? Because if you add heat to a gas, what happens? Sorry, let's try a liquid. Let's add liquid heat to a liquid. Turns into a gas. What happened? Chemical or physical? Physical. Okay? We have physically changed the atoms from being close to each other to being apart, or sorry, molecules from being close to each other to being apart from each other. But the chemical composition is still the same. But if we take 2 liquids and we mix them and now we see a gas, we didn't supply that energy. Okay? All we did was mix them. That external energy was not supplied by us, and now that when we see those bubbles or that gas formed, that is now a chemical change. Because the energy to cause that change was supplied by the molecules changing the arrangement of their atoms. Yes?
What if the mixing of the chemicals is an exothermic reaction that then causes a phase change?
If it is an exothermic reaction, we would move to number 4. An energy change is observed. So when we mix the chemicals and the temperature changes on its own, where did that energy come from? The molecules changing the arrangement of the atoms, releasing that energy. Okay? So if we really push your example to the limit, we mix 2 chemicals, an energy change is observed, and now a gas is formed. Okay? Well, how was the gas formed? Was the gas formed based on the energy that the reaction supplied? If that's the case, then the gas forming is a physical change. Okay? Whereas because the heat came from the reaction, that's now a chemical change. So we can break down individual observations into both chemical and physical changes depending on when and how they are happening. Okay? So we have seen the gas forming reaction. You see that with carbonate. Okay, the carbonate ion, when you add an acid to it, put hydrogens next to it, and make carbonic acid, carbonic acid is highly unstable and it decomposes fairly readily into water and CO2. What phase is CO2? A gas. There's our bubbling. Okay? So once we form the carbonic acid, it goes through a secondary chemical reaction to give us that physical observable. The other big one that we could see is a solid being formed. So if we take two clear solutions and we mix them and now we see a solid, okay? For us to form that solid phase, we either had to remove energy from the reaction based on our interpretation, okay, what we did with it, or the chemicals in themselves change the arrangement of the atoms and change their physical or their chemical properties, the solubility. Okay? I do want to make one caveat or one extra thing there. When we say clear, okay, clear does not mean colorless. You can have a clear yellow solution. Okay? For lack of a better example, urine in most cases is a clear solution. Hopefully it's always clear. Okay? But it is yellow. Okay? You can still have a colored clear solution. Okay? So when we mix these and we form that solid, it's typically referred to as a precipitate. Just an extra little vocab word. The next one is a permanent color change. You've got to be a little bit careful with your color change one. If I take a red dye and I mix it with a blue dye, what color do I have? Purple. I go, oh, well, that's permanently a color change because it's now permanently purple. Is that a chemical change? No. All we did was mix those two colors and we're seeing a different response. So your color change can be a bit of a gray area one as well. You got to watch out for that one. Okay? So we're looking at drastic big changes in color that we couldn't predict based on just mixing of things or even dilution. If I take a yellow solution and I mix it with a clear solution, the end result looks like the clear solution changed color. Okay? But all that really happened is we mixed the yellow one with it. It's not a permanent color change. Where did you get those slides? I think I didn't even post those. Or maybe I did. Oh, I forgot. We got some images here. So our very first image, you're looking at a gas form. So they're trying to show bubbles at the top of that surface. We can see a precipitate. In this case, you see that yellow. That's not a clear solution. How do you know it's not clear? You can't see through it. Okay? So if you see a cloudy solution, what does that mean? There's a precipitate. Okay? You can see it precipitate to varying extents, but that's ultimately a precipitate. Okay? Let's see, where are we now? When we move to the energy change, okay, there's a couple big reactions that give us energy changes. If we mix two clear solutions and we get an energy change, most cases what we're looking at is an acid-base reaction. Acid-base reactions are very exothermic. They release a lot of heat. Okay? So if we look at the release of heat, we can call them exothermic. The sign on the energy, which we've talked about before with our bond energies, is negative. Okay? If our reaction absorbs heat, that's endothermic. We're going to get a positive energy. Okay, what about light? Is light emission an energy change? Yes, light is a form of energy. If light is released from the mixing of two chemicals, we are looking at a chemical change. Okay? Questions about our chemical reactions? Okay. Oops. It is related to breaking bonds and making bonds. Ultimately, when we do a reaction, we are making and breaking different bonds. Okay? You will see both positive and negative energies when we go through and do individual reactions. So it's different from bond energy. Bond energy is the formation of a bond from two atoms in their gas phase. When we look at a chemical reaction, we are making and breaking bonds that are not in the gas phase. So we can't look at the energy relationship that we saw with bond energy. Okay? It's not directly related, no. Okay? Now what we're going to do is take a look at reactions. Okay, so if we take a look at the states of matter or look at an individual reaction, what information is provided in this equation? What do we see? What? Oh, you see aqueous. aqueous is a tip-off that we have an acid, but what's the other thing that we need to have an acid? Hydrogen. Do we see hydrogen with D? No. So we can't, it's a reasonable assumption, but we don't know what D is. So if there's no hydrogen there, we don't have an acid. Okay. What did the AQ mean? Aqueous. So we've got some information about D. D is dissolved in water. What other information do we see in here? What does the S mean? In this reaction, C is a solid. L is liquid. Anything else? G is gas. The enthusiasm on that gas statement was pretty awesome. Okay. So we have phase information in an individual reaction. As fun as it may be to include phases, it's usually pretty horrible, and being sarcastic at least is the fun part of it. Unfortunately, you guys will have to specify the phases on everything. When you go through and write out an equation, you must specify the phase. Okay? And we'll get into knowing what those phases are in a little bit. Is there anything else in this? Okay. Kind of a good approximation. We're looking at this arrow being equated to an equals. It's not exactly an equals. We can, sorry, just a sec. We could look at a relationship in mass. The mass on the left side must equal the mass on the right side. The atoms on the left side must equal the atoms on the right side. And that's a big portion of this chapter. Sorry, Heidi, what was your statement?
No, I was just saying if you add the gas and the liquid, it produces the solid and
Getting to the biggest conclusion out of the equation. Okay? If we mix A and B, what happens? We get C and D. What does that mean? The left side of our equation are reactants. It's effectively what we are mixing. What is the right side of the equation? Our products. It's the result of that mixing. Okay? So what we're basing everything on is that center arrow deciding what makes a reactant and what makes a product. For our individual experiments, we would take our reactants and we would mix them together, and then something would happen, and we would then look at those products and see what those products were. So it's the basic structure of all equations that we're going to see this semester and any chemistry semester. Okay? Questions about it? You guys all comfortable with the pieces within it? Good. Your textbook lists off a bunch of other symbols that you could go through and see. You'll notice that we've got RS, LG, and AQ for defining the individual phases. Okay? You'll notice AQ we are specifying as a phase. Okay? Why would we define it as a separate phase from solid, liquid, and gas? Specifies that there's also water present when we go through and do the reaction. Okay? That's a pretty important thing to include. If we wrote water in the reaction, what makes that a little bit more dangerous is that we're implying water is a reactant. Well, if we write AQ, we're saying water isn't involved in the reaction. All it's there is to keep everything mixed. Okay? So it's not involved in the bonding, bonds breaking and making, at least directly. Okay? Other symbols that you can see, we've got our arrow looking at defining our reactants to the left and our products to the right. We've got our plus. I guess I didn't do the plus. What's our plus meaning? We're just adding things together. Okay? I want to be a little bit careful with reacts with. According to our equation, are we really saying that second plus is a reacts with? Not really. All we're saying is that it's also there. Okay, so the plus just means it's present. Okay? Would we ever expect to see a minus in a reaction equation? Okay. One of the nice things about reaction equations, this is why chemists are cool, no minus signs. Your balanced reactions will never have a minus sign. When we talked about energy, we said energy could come in with a minus, but what did that minus mean? Negative energy was what type of a reaction? Exo or endothermic? Exothermic, which meant that heat was released. How would we specify that heat? As an energy on our product side. It was released in the course of that reaction. What if it was a positive value? Then it was a reactant. It's still going into our equation as a positive sign. Okay? The plus minus sign just meant which side of the reaction does it go to. That's it. What was your question, Thor?
No, you got it.
Okay. The next two arrows right in the middle, I don't think we'll see too much of this semester. That delta symbol, what did that mean? Change. What is it meaning in this case? A change in temperature or heat. Okay, so if you see that delta symbol, that means we've added heat to the reaction. The other one, okay, we see Fe. You're right, iron was added. Why did we not put it in front of the arrow? Okay, well, what is a catalyst? Very true. So what we're saying with our catalyst is it's not actually consumed in the reaction. So we don't want to include it on the left-hand side of the equation, because what would happen at the right-hand side? We'd also have to include it there, because it's neither consumed nor produced. So if I put it on the left-hand side of the arrow, I have to put it on the right-hand side of the arrow, which means I have to write it twice. Okay? Be lazy, write it in the middle. Now it's a catalyst. Magically, we don't have to worry about it anymore. Okay? Questions about any of that? Okay, when are we done? 40, right? Good. Okay, so chemical reaction. Wow, I thought I stepwise this. Sorry, this jumped out pretty fast. This was definitely supposed to be stepwise. So we can take a look at the chemical reaction to start off with. What are we saying? So if we converted that reaction into words, I'm definitely not going to write it out because that's going to take way too long. All right, well, we'd start at the left-hand side and we say sodium hydride or solid sodium hydride. How do I know to say that? It says S, so that means it's solid. How do I know to say sodium hydride? Because I'm bomb at my nomenclature. Okay? So you have to be able to know your nomenclature to be able to draw the individual structures or to refer to them. On the test, I may just give you a sequence of words, and you have to convert that into the proper equation. Okay? So you have to know your nomenclature. So solid sodium hydride is mixed or is reacted with or is added to, what's the next one? Acetic acid, which produces sodium or aqueous sodium acetate and hydrogen gas. Okay? The main reason why I picked this reaction is that last guy up there. How do we know that's hydrogen gas? So the G says gas, absolutely. Why is it not written Hg? There are some elements that in their natural elemental state are not by themselves. They must have a covalent bond to the same type of element. Those elements are known as diatomic molecules. Hydrogen happens to be one of those. So in the phrasing, if we said we produced hydrogen gas, guaranteed your multiple choice answers, let's see, how do I want to do this? Let's just erase all that. If we looked at which of these is hydrogen gas, you would probably see both of those options. Which is the correct answer for hydrogen gas? B. Because hydrogen in its gas state needs to be H2. How would we ever get A? Have to change our wording around a little bit, and we could say an atom of hydrogen in its gas state. Okay, so we have to add a lot more information to that to imply it's hydrogen by itself, okay, also in the gas state. So you got to be very careful with that. So which molecules are diatomic? Okay, well, unfortunately, you have to have these memorized. So we've got some memorization devices. There's 7 of them. If you take a look at hydrogen being on the far left, and then you can go to the periodic table, nitrogen to fluorine and straight down, you kind of have a 7 symbol, sort of. I mean, right? So if you memorize, hey, there's my 7 plus 1. Okay, that can work as a possible device. The one that for some reason has stuck with me for I have no idea how long is this phrase, have no fear of ice cold beer. Have gives you hydrogen, no gives you nitrogen, fear, fluorine, oxygen, or of oxygen, ice, iodine, cold, chlorine, beer, bromine. Okay. Up to you, however you want to go through and have that memorized. You are expected to know that if I say give me a molecule of bromine gas, you will give me Br2. Okay, you have to specify that subscript. Okay? As far as deciding the phase, you can look at the colors. Okay? I said bromine gas, but we could also look at bromine as the liquid's phase. Okay? Questions about these? Okay, where are we? So let's push this a little bit further, going into, oh, sorry, yes.
So I noticed on the aqueous, which generally means a gas, right?
Aqueous does not mean gas. Aqueous means, aqueous means, what does aqueous mean? Dissolved in water. Acids, to be an acid, has to be dissolved in water as well. But just because you're aqueous doesn't mean you're an acid. Okay. Other questions? Okay. So balancing chemical reactions. When we look at an individual reaction, we go all the way back to probably chapter 1. One of our rules was conservation of energy, conservation of matter. So when we look at a reaction, we have to make sure that we don't create or destroy matter. Okay, so we could look at mass, which is a bit tedious, particularly if we're not given any mass information. Our balanced equation is going to give us or imply some of that mass information, because if I have a hydrogen atom, what do I know about its mass? It's 1. And at this point, we could say 1 AMU, because we haven't talked about any other bigger mass units. So if I have, on the left-hand side of this equation, 2 hydrogens, what's the math? Sorry, I can't do that math. 1, 2, 5 hydrogens. What does that mean has to show up on the other side? 5 hydrogens. I cannot create or destroy that mass. It must still be present. Okay? For our sake, thankfully, we won't create or destroy atoms either, at least in this class. Okay? So if you see 5 hydrogens on the left, you need to see 5 hydrogens on the right. Does it matter where those hydrogens are connected? No. As long as they're present, we don't care. Okay? So what we can go through to balance is start with any atom we want. Okay? In this case, I picked hydrogen just because we've been talking about hydrogen, which was kind of a bad choice because I would recommend you don't start with hydrogen. Okay? But we can go ahead and start with that anyway. How many hydrogens do we have on the left-hand side of our equation? 1, 2, plus 3 hydrogens gives us 5 hydrogens. How many do we have on our product side? There's our 3, 4, 5. Our hydrogens are balanced. We don't say, oh, now the equation's done. No, we have to go back through and check all the other ones as well. So let's pick another atom. Sodium. How many sodiums do we have on the left-hand side? Right-hand side. You guys are going too fast. Carbons. Isn't that 2? Okay. For those of you saying 3, can you check that for me real quickly and tell me why you're getting 3? Carbon should have 2. How do we know carbon has 2? That subscript right after it only applies to the atom immediately in front of it. So that carbon, there's only 2 carbons. Yes?
Does it acetate, do you ever see that break apart? At least
I'm going to address that after we balance it this way. How about carbon on the product side? And our last element, oxygen, 2 and 2. We've now verified that our atoms match up on both sides of the equation. Everything's good. We're happy. Okay, our equation is now balanced. Are there easier ways to approach this? So answer to that, Thor? Yes, there is an easier way to approach this. Okay. We can evaluate our complex ions. We broke apart, okay, into each of these individual pieces. But we could also go through, instead of looking at each of the individual atoms, look at the complex arrays. Look at our subcategories. So we can break here, and here, here, and this one's a little bit weird because it's not written nicely, and there. Okay. Why go through and break it this way? Well, now when I go through and look, what happened to the sodium? 1, and on the other side, also 1, right? Okay. Remember how I said skip hydrogen? Hydrogen and oxygen are the 2 elements that you should save for the very, very end. So what I'm going to do now is jump to the next thing that I can use to balance. What thing is that? Acetate. Okay, why can I do this? Well, what happened to C2H3O2? How many of those do I have on the left? I have 1 of them. How many do I have on the right? I have 1 there as well. What's that? At this point, balancing, no. Aqueous is for your final overall equation. Okay. Why does this help us out at all? Now, instead of having to balance both the carbon and the oxygen as separate units, I can balance them as 1 unit. We have to be a little bit careful, because the last thing we have to balance is hydrogen. How many hydrogens are on the left-hand side? Why is it only 2? We've accounted for the hydrogen in our acetate already. Okay? I personally like to go through the complex ion balancing because I can eliminate more atoms quickly. However, you cannot double count. If you double count, you're going to run into problems. Okay? So if we look to the left-hand side, how many hydrogens now? We just have those 2, still balanced. I don't know why H equals H. That should be H equals 2. Okay? We'll pick up, let's see, because I think the next slide is, maybe the next slide is rules. Yeah. We're going to start with balancing on Thursday. We're going to do a couple examples with that, and then we're going to push into just looking at all of the possible reactions. So we're not going to do a lot of balancing reactions right away, because we're going to look at balancing each of the chemical types of reactions as well.